episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome, everybody, again to another episode of our show with another truly fascinating guest who is helping to create a better tomorrow for all of us. We have the honor today of being joined by Dr. Jill Tarter, who is Chair Emeritus for SETI Research, or Search for Extraterrestrial Intelligence, at the SETI Institute, which is a nonprofit research organization whose mission is to explore, understand, and explain the origin and nature of life in the universe and apply this knowledge gained to inspire and ultimately guide present and future generations. Dr. Tarter received her Bachelor's of Engineering Physics with distinction from Cornell University, her Master's and Ph.D. in Astronomy from University of California, Berkeley, served as the project scientist for NASA's SETI program, the High Resolution Microwave Survey, and has conducted numerous observational programs at radio observations stations worldwide. Since the termination of the NASA SETI program back in the early 1990s, she served in the leadership role to secure private funding to continue this exploratory science, currently serves on the management board for the Allen Telescope Array, which is an innovative array of around 350 antennas, which will simultaneously survey the universe for known and unexpected sources of various astrophysical emissions and speed up the search for radio emissions from other distant technologies by orders of magnitude. Dr. Tarter's work has brought her wide recognition and awards in the scientific community. She is deeply involved in the education of future citizens and scientists and is a frequent speaker for science teacher meetings at museums, science centers, and she's extremely committed to science and education for teachers and the public. And most people are familiar with her work as portrayed both in the Carl Sagan science fiction novel and the movie Contact starring Jodie Foster. And she's also the subject of the book Making Contact, Jill Tarter and the Search for Extraterrestrial Intelligence by Sarah Scholes. Dr. Jill Tarter, thank you so much for taking the time to come on the show today.
Well, it's my pleasure, Ira. I have to correct you on one thing, though.
Please do.
We had hoped to build 350 dishes in the Allen Telescope Array. But by the time we finished doing all of the technology development, we only had enough money to build 42. So if someone wants to write a check, we could get going and finish out the 350. But at the moment, we have 42 dishes.
I'll say, and those are the ones behind you, and they look very nice. But we'll hope to get that message out there for you. Definitely. I'd love to just, take a little time, give you the floor. I was looking through your publications over the years, and it was very interesting that you started publishing in the scientific literature on the SETI ideas, I think as far back as 1977. Can you just take us back on a little bit of the journey on when you really got involved and passionate about this particular theme, and then also at the time, what was it like? Was there a sort of real life David Drumlin in your world that was against what you were doing then? Talk us a little bit about the early days.
Well, Ira, I can remember very clearly as a kid walking along the Gulf Coast of Florida in the Minnesota Key. We'd visit my relatives once or twice a year down there who were literally beachcombers. And I'd walk along the shore with my dad, who had studied astronomy at Swarthmore. And he was trying to teach me the constellations. And it's just such a dark sky, right, down in the Keys at that time. And looking up at the sky and just being quite sure, I don't know why, but I was pretty sure that on some planet around one of those stars in the sky, there would be a small creature walking along the edge of an ocean with their parent, seeing our sun in their sky as a star. And it just seemed to me that was a worldview that was very appropriate, that there would be life on planets around other stars. And I didn't do anything about that. I went and got an engineering degree, and then I went to graduate school at Berkeley and got a degree, a PhD in astrophysics, and talked about these objects that I named brown dwarfs, which are actually stars that are too small, too low mass to ever burn hydrogen to helium stably and shine. So they essentially go out. And I was trying to help the observationalists know how to find them by making a model and predicting a color temperature, so that astronomers would know what to look for. And I was never successful. The opacity tables at those low densities and temperatures at the time were terrible, and I could never model an atmosphere onto my stellar core to figure out how the light would come out and what the color would be. And so the time I heard Edmund Land of Polaroid say brown is not a color. And so I said, okay, well, they're going to be brown dwarfs, right? Because I don't know what color they're going to be. And then I was a graduate student for a very long time. It took me many years to get my degree because I was raising a daughter. And when I first showed up at Berkeley, I was given, supported by a research assistantship that had me programming the first desktop computer that we ever had. It was a PDP-8/S, and I used to joke that it took 2 people to get it up on the desk, but once it was there, it was all ours. And there were 11 instructions, and I had to learn how to program this computer in Octal because there was no language.
Sure.
And many years later, that piece of equipment was given to an X-ray astronomer whose name was Stu Boyer, who had an idea about using UC Berkeley's radio telescope at Hat Creek in Northern California to do a SETI search. And Stu and Mike Lampton figured out that because in radio astronomy you detect both the amplitude and the phase of an incoming signal,
sure,
you can therefore essentially make a noiseless copy of the data, right? And so Stu realized that, well, while the radio astronomers were using this telescope to look somewhere at some frequency, we could use their data and analyze it for engineered signals rather than astrophysical signals. Really clever idea, right? The correct term is doing commensal observing, although we didn't know that word at the time. And so Stu didn't have any money. So he went asking and begging for donations, and somebody gave him this old PDP-8S, and he said, well, what the heck do I do with this? And they pointed down the hall and they said, Jill's still here. She used to program that. And so he came to my office with something called the Cyclops Report, which had been done 2 summers before at NASA Ames as a ASEE summer study, giving engineering professors a blue sky project and telling them to find a solution. How would you do this if money were no object? And so what came out was the Cyclops Report. And this was a suggestion of how you might find evidence of somebody else's technology. And it was build 1,600 100-meter dishes in the radio and listen for signals. So Stu came to my door with this Cyclops Report as his recruiting document and said, do you want to join our team? Right? We're going to try and do this experiment. And I read the Cyclops Report. I think it took me better part of 24 hours. I just was so unbelievably intrigued by this idea that after all of the millennia of humans asking, are we alone? And they asked the priests and the philosophers, suddenly we could get the scientists and engineers involved and actually do a systematic scientific exploration to try and answer this old question. And I just got hooked. I thought, that's so cool. And here I am, and I'm in the right place with the right set of skills. And so I said, yes, sign me up. And I've never looked back. And it was a very fortunate accident. And we started by programming that old computer, and we started with commensal observations at the 85-foot telescope at Hat Creek and went from there. So I'm in this business because of a very fortunate accident.
Outstanding. Outstanding. And when you, aside from the education and the outreach component of SETI, there is the Carl Sagan Center, and is made up of various groups: astronomy, astrophysics, exoplanets, planetary exploration, climate and geoscience, astrobiology, and SETI, all which sort of form the sort of foundation for what you write about, called observational exobiology, which includes just everything from the synthesis of the building blocks of matter in stars to their disposition on a planet, to some biogenesis, to some evolution, ultimately a advanced civilization that can send signals back, which we will hear via SETI. Could you talk a little bit about how all those groups, do they always work together very well from the beginning? I think sort of, in my time in the industry, everything's very siloed, and people, I was in the pharmaceutical industry, and, the toxicology people didn't always like to work with the pharmacokinetics people and so forth. Did it always work smoothly at the beginning, or is this something that you sort of optimized over time in all these pieces that make up observational exobiology?
Now, Ira, when I co-founded the SETI Institute back in 1984, I looked at the Drake equation, which is an equation that you cannot use to calculate anything, but it is a lovely way to organize our ignorance about this question of life beyond Earth. Yep. And I wrote a charter that said that we would be pleased to be the research home and support group for scientists working on any of the terms in the Drake equation, anything to have to do with origin, evolution, distribution of life in the universe. And we did this in 1984. We formed the SETI Institute as a way to save NASA money, as it turns out. And we got around the fact that there were no civil servant slots for doing SETI. We were getting all of our talent as soft money contracts with professors at all of the universities in the Bay Area. And at the time, the indirect cost for issuing a grant to a university was more like 100%. Mm-hmm. So it was very expensive to get our researchers in this manner. And we realized that if we formed a nonprofit and all of these professors became our employees, then in fact we could charge an indirect cost rate that reflected the true cost of doing business, which was more like 20% rather than 100%. And instantly, once we did that, we saved a great deal of money that we could put into more research mm-hmm. and instrument building. And so this was a really good idea. And it turns out that there are a lot of entrepreneurial scientific researchers, a lot of them in the Bay Area, who jumped on board because they wanted to stretch their grant dollars farther. And so it just became extremely successful. And we always had this cross-disciplinary focus at the Institute, and our colloquia series was wide-ranging. Folks would literally meet up around the drinking fountain and discuss things from different points of view. We found it very congenial to have all of these different disciplines under one roof, to look at the same kinds of questions from different points of view. I don't think any of our scientists came in and found a corner and sat there and just worked on their own stuff and didn't talk to any of the rest of us because they weren't interested in our topics. Mm-hmm. It was a very fortunate and beneficial environment, right? So we now have, I think the last count, we have 106 or 107 Ph.D. scientists associated with the Institute, doing all kinds of different research tasks, from bodies in our solar system to exoplanets around other stars. we've, in my career, there have been two amazing game changers. So when we started all of this, we had no idea whether there were actually planets around other stars. We hadn't found any. We didn't know. And there were two competing theories about how planets might form. And if one of them had been correct, planets would have been very, very rare. Turns out that wasn't the correct explanation for how planets form. And planets are the natural outcome from star formation. And we now know, thanks to Kepler and the ground-based radio velocity studies, that there are more planets than stars in the sky. So that's one game changer, exoplanets. The other game changer was extremophiles. Because back when we started the SETI Institute, the wisdom said that life could only exist between the boiling and freezing points of water. It had to be very neutral in terms of its pH. It couldn't be too acidic or too basic. It couldn't. The pressure would have to be like the pressure on the surface of the Earth. And it just, all of that was so wrong. And we began in the 80s to understand how wrong it was when we began to discover extremophiles, organisms living in environments that are totally inhospitable to humans. But these organisms had evolved over millions or billions of years to be absolutely at home in boiling battery acid, for example. So extremophiles and exoplanets, two incredible changes of perspective over my career that make it really much more reasonable and almost inevitable now to ask the question of all those potentially habitable worlds out there, are any of them actually inhabited? And I think because we ended up from the very beginning having to unlearn all of these things that we thought we knew, but which were wrong, that made it all the more likely that a biochemist would talk to a geologist about the conditions for life. And, well, what if it were like this? Could somehow life survive? And so it's really been phenomenal to have this very vibrant and multidisciplinary group of scientists working under one roof. Now we're all under our own roofs, right? And sitting here remotely, but it's been very fruitful.
It's interesting, the point about extremophiles, because about a year ago I had the opportunity to spend some time with Penny Boston at NASA right before she was retiring, and we were talking about all sorts of fascinating things that she's finding in caves and so forth. It just brought the thought that that whatever, several months ago, there was this team that made this report about this phosphine gas on Venus, and I know that it's somewhat questioned now, but here was this marker of anaerobic bacteria that make the stuff here. Okay, there's some there. When you talk about the extremophiles and some of the weird things that we're learning they do, like Deinococcus, which likes to swim around and all this radioactive waste and all that, does that sort of broaden the scope of the exoplanets that maybe a couple of years ago, we're not going to look at that because nothing lives in whatever battery acid rain or an ocean of radioactive junk, but maybe we should look at those planets again because X, Y, and Z organisms, which we never cataloged, we just found them at the bottom of such and such cave or the bottom of the ocean. Has that expanded? Has the extremophile part of this sort of expanded what you look at in terms of those biosignatures or whatever, what proper terminology for this is, but has that expanded that a little bit?
Oh, absolutely. Yeah. And that's been exciting to see that happen. So phosphine in the clouds of Venus, well, two questions. Have we got the right molecule? right? Because it's only a single line detection.
Right.
And then secondly, have we actually really, without exception, looked at every potential chemical pathway, this huge network? And can we say absolutely that we can't make that gas under the conditions that it is, in the abundance that it is, without some kind of life or biology involved? And so those are the questions, and we haven't fully answered either one of them yet. So we have gotten this evolution idea somewhat backwards through history. We have entrenched in our minds this idea of the ascent of man, right? That somehow we are the pinnacle of evolution, and that couldn't be farther from the truth. This is a bacterial universe, right? And so we are just one little twig on this very robust either tree or bush of life. And so even though we know now about chemically, biologically, at the molecular level, how evolution proceeds, and we know that it isn't directed, that it's opportunistic, we somehow can't get away from this privileged position in which we place ourselves, even though nature doesn't agree with that at all. So it's a wrong mindset that we've had for a long time, and I think that's actually impeded what we have learned, because we don't go looking somewhere else, because we know that, well, that wouldn't have been good for us, so can't have been good for anything that's interesting or worthwhile. So yeah, we need to get over ourselves in terms of understanding evolution.
Absolutely. Couldn't agree with you more on that one. I've heard you talk on some other shows, what you referred to as sort of this 9-dimensional haystack that you've had to work in over the years. You talk about 3 spatial dimensions, time, and then sort of frequency, modulation, sensitivity, wavelength, a lot of these components of the electromagnetic spectrum that you study. I'm sorry if I'm going to contact, and I'm talking about Jill Tarter, not Ellie and Arroway, but right in the movie, there was your character, listening, and then there was a bunch of computers doing some stuff. Can you talk a little bit about how the technology for looking at those dimensions, those 9, in that haystack, have evolved, improved over time? Now we're hearing about tools, artificial intelligence, machine learning, things of this nature to help us with our exploration in different domains. And talk a little bit about how these tools have evolved throughout your leadership of this area.
Well, yes, our search is getting faster exponentially, mainly because of the improvement in computing technologies. So when SETI turned 50, I got tired of people saying to me, well, you've been doing this for 50 years and you haven't found anything, therefore it must be that there's nothing to find. And so I tried to say, yeah, we've been looking for electromagnetic signals, and we don't even know that that's really what we should be looking for. Maybe we should be looking for zeta rays. I don't know what a zeta ray is. We haven't invented that technology. There's nothing I can do about that. We'll just try and keep going until we do invent zeta rays, and then we'll look for them too. So I wanted to try for a larger audience to express just how large this cosmic haystack is that we're trying to search within for a needle. And so, yes, I came up with 9 dimensions: space, time, polarization, modulation, sensitivity, for wavelength, etc. And I put some loose limits on how big each one of those parameters might be, with the range of parameter that space that we might have to investigate. And I multiplied them all together and came up with a 9-dimensional volume, and my brain isn't good at, figuring out what 9-dimensional volumes look like. So I said, okay, let's just do this example. Let's say that the volume of space, spatial parameters that we need to explore to find potentially an electromagnetic signal, let's say that 9-dimensional volume is equal to the volume of all the Earth's oceans. How much of that ocean have we explored?
Mm.
And it turns out it's a few parts in 10 to the 23, which doesn't mean much to anyone, but it turns out it's essentially a glass of water
There you go.
out of the Earth's oceans. So I thought that was a good way of trying to make the point that we've hardly begun to search, which is bad news. But the good news is the search is really improving at an exponential rate, right? Because primarily of computing capabilities. Our telescopes are within a factor of 2 to 3 of being as good as you can make them. Mm-hmm. But our computing had improved by 14 orders of magnitude since the original start. So, okay, that's a glass of water when SETI was 50 years old. Then 10 years later, the students at Penn State decided to redo that calculation. Mm. And now they said, oh, it's kind of like a hot tub or small pools worth of water. So in 10 years, we've gone from a glass to a small pool. Mm-hmm. And that's a very visual example of how things are improving. And in an exponential situation, all the good stuff happens with the last factor of 2 of improvement, right? And so we're trying to make a point that perhaps we shouldn't be surprised that we haven't succeeded, because in some sense we've just begun to look.
And continuing on that line, you've also talked about the electromagnetic spectrum is vast, but there's other stuff. There's gravitational waves. There could be some civilization that made some weird hypothetical megastructure that's warping gravity, or something else that I was reading about. There's this hypothesis about if there's new fusion technologies out there that have different neutrino signatures. If infinity dollars all of a sudden fell from the sky, would you put it in millions of more of the Allen array type telescopes, or what are some of the other, obviously the non-existing stuff that we haven't thought of yet, but what are some of the other areas that, even though hypothetical now, that you would love to throw some of that infinity dollars at if it existed?
Well, we've begun, because SETI has a lot of history, right? Mm-hmm. And in some sense, a lot of baggage given the roller coaster of federal funding. We've actually begun using a term that we call Techno Signatures. Okay. And in a way, we're trying to make a parallel with biosignatures. Mm-hmm. And the field of astrobiology, in our opinion, should be an umbrella for both biosignature and technosignature research. Mm-hmm. So what might be a technosignature that isn't an electromagnetic signal that's obviously engineered? Well, here's an idea. So we now know about exoplanets because of transits, right? Where a planet passes in front of the star from our observational position and dims the light a little bit. Yep. Well, now the IAU tells us a planet has to be round. Right? We went through a whole lot of song and dance a while ago about defining a planet. So the fine structure of that light curve as the transit starts and then as it ends is going to be defined by the shape of the object that's blocking the light. So what if somebody with sufficient technology orbited planet-sized triangles or Venetian blinds in front of the star? Then the higher order moments of the light curve, just at the beginning and the end, would allow us to see that the shape of what was causing this dimming of the light, this transit, wasn't round. That shadow wasn't round. So something other than a planet. That might be a techno signature. How about when we get the ability to image individual planets in an exoplanet system, such as the beautiful TRAPPIST-1 system that has 7 Earth-sized planets orbiting a tiny little dim red star? What if, when we can image the planets, we find that their equilibrium temperatures are not falling as you go away from the star, as they should? The farthest planet should be colder than the closest one. What if they're not? What if when we image those planets, we see that they're all the same, or 3 or 4 of them are the same? Shouldn't be, not naturally, but with geoengineering, astroengineering, they might be. They might have been modified to be more comfortable for some technological species there. That would also be a techno signature. So we can think about things like this, and then what you would do with your infinite dollars is support all kinds of astronomical exploration of the sky, looking with new tools in new ways with greater sensitivity, and then looking at the results and saying, that's strange. What might be doing that? And I think you'd learn a lot more about the cosmos, and you might also learn about some extraterrestrial engineers.
And in between sort of the advanced extraterrestrial engineering species that's a million years ahead of us, or the microbes, do you spend much time thinking about what I'll call sort of the, and this gets back to our earlier discussion about the pinnacle, about sort of the in-between, the life in the middle? We're learning so much about life on this planet, not just the extremophiles, but the tardigrades, which can do some amazing things in terms of survival, in terms of intelligence. The octopus, which we thought was this bumbling mollusk for so many years, now we're realizing it has 9 brains, and it has the way it processes information totally different than we've previously expected. We have organisms on this planet that don't have brains. We have organisms on this planet that don't have nervous systems technically. What do you guys do in terms of the astrobiology about the sort of the mid-ground? Also thinking that there are going to be species possibly that, if that technologically advanced civilization does not sort of get through the technological adolescence, as you talk about it, and destroys itself with the zeta rays or whatever they invent in the future, there could be other stuff around that's not microbes, but isn't technological. Do you give a lot of thought to that area of the astrobiology equation ever? And what are some of the pie in the sky ideas that you?
No, that's the reason we talk about techno signatures. There could be planets that are water worlds that are inhabited by whales and dolphins that write or sing poetry and are very, very clever, but I'm not going to find them. I'm looking for technology. And if I find the technology, I'm going to presume that at least at some point there were technologists who created that technology. Sure. They might not be there anymore. They might have moved on, done themselves in, but the technology remains. I mean, I like to point out to people, we make glass today exactly as the Romans did.
Mm-hmm.
That technology has certainly outlived the creators of it. So for me, actually, the reason to work on SETI, in addition to trying to answer this old question that seems inherently important to humans, is because we won't succeed unless, on average, technological civilizations or their technologies are long-lived, right? Because to be successful, two technological civilizations have to be close enough to one another to discover each other.
Sure.
But that's not only close in space, it's close in time. And so for us to be cotemporal with another technological civilization in this 10 billion year history of the Milky Way galaxy, then the lifetime of a technological species or the technology has to be very long, so that across 10 billion years, two of them are cotemporal overlap in time. And so for me, the real payoff of a successful SETI program is the fact that we learn that it's possible for us to have a long future, because on average, other civilizations have done so. Phil Morrison, one of the first pioneers in this field, used to refer to SETI as the archaeology of the future. So it's archaeology because if there's any information contained in a signal that you detect, the tyranny of light speed means that you're learning about their past by the time the signal reaches you. But the fact that you found a signal means that you can have a long future. So I find that really inspiring. That's the reason I've stayed hooked on this exploration all these years.
And talk a little bit about, I was reading about this, I think it was a SETICon meeting back in 2012, where I think you had a little back and forth with Stephen Hawking about alien invasion and all this stuff. And I was for the position that, just like in any of these movies that we see, if there's a species that can master interstellar travel and inexhaustible sources of energy and so forth and so on, they don't need to come here for food or oil or whatever they usually come here for in the sci-fi movies. When did all that begin, and sort of this alien invasion, sort of the Hollywood picture of this stuff? Obviously, it's not what we see in Contact. That goes in a different direction. But talk a little bit about that part of this, if you would.
Yeah, well, I think it began back in the 40s with the first sightings of saucers, flying saucers. And then we look at ourselves and we see how we behave, and we think that we know that we do some really stupid, terrible things. And we fight over trivial differences among humans globally around this planet. And so I think we were just channeling ourselves with all of that alien invasion. And, Stephen pointed out that it didn't, when Columbus showed up in the New World, it didn't work out very well for the natives. So I have a different idea, and I have no idea whether I'm right or Stephen's right, and we won't until some future where this may happen. But it seems to me, if you're worried about them coming here, then they are more advanced technologically than we are.
Sure.
Means that they're going to be older. And I don't understand how you can become an old technological civilization unless you outgrow the aggressive tendencies that probably helped you to become intelligent in the first place. So I'm in the Steven Pinker kinder and gentler, cultural evolution, right? once we began to establish a rule of laws, we were less likely to settle our grievances by hitting somebody over the head with a club.
Mm-hmm.
So I think that cultural evolution will lead us to be better, less aggressive, and therefore it seems to me that the older technology that can get here is less likely to be aggressive, right? I don't think they can sustain themselves if they don't outgrow that aggression. Don't know, but that's my guess.
The day we have formal confirmation that we are not alone in this universe, psychological, philosophical, religion, so forth. Talk a little bit about what, whether that's in 2022 or 2052, whatever it happens, what happens over that next year, let's say, on this planet. What types of things are going to be going on?
Well, first of all, we have to admit that it may never happen. We could be singular. In in physics, you count 1 to infinity.
Sure.
When you have only a single example, it might well be unique. The moment you find a second example, you know there are many.
Mm-hmm.
So we're still in the N of 1 situation. So maybe it never will happen. Maybe we are alone. But if it does happen, I think it will change all kinds of things and change them very quickly. So the thing that I worry about is creating another have and have not situation.
Okay.
Because if the direction on the sky from which an intelligent signal is broadcast, if that is positioned too close to the poles, then you might have nation states which have no real estate on which they could build their own observatories to study this phenomena, right? And so I can see that providing a new tension that we certainly don't need, right? We at the SETI Institute have always said that any information that is being transmitted is the property of all humankind, right? It's not being sent to California, it's being sent to the planet. And so we should share it, and that would be our intention. But I think that given the fact we're still in a nation state configuration on this planet, and there is maybe not enough trust, every nation would want to acquire the data itself. And of course, if there's a signal that's continuous and we're on a rotating planet, you're going to need lots of different longitudes in order to continuously cover the signal. But if there's a latitude problem, that could create a tension that we don't want. So I think that we'd have to figure out some way to build an orbital observatory that would dispense information globally.
Got it. Joe, what are your thoughts about sort of the genetic, let's say the genetic colonization of space? So, there's a lot of ideas floating around out there about, we're in this world now of synthetic biology and all these tools for creating DNA on demand and so forth. Should we be genetically colonizing space at this point? And are we once again, coming back to this this pinnacle concept again, should we be the ones going? Or do the extremophiles, do the tardigrades, do other organisms who have sort of evolutionary benefits, let's say, deserve the first trips, whether that's to Mars or moons and Jupiter or beyond. Just like to get your thoughts on some of these ideas in terms about sending stuff out.
Yeah, well, I think the robots should be the first to go.
Robots, okay.
So that we can, in fact, explore what is native to any particular body, right? We co-evolved with this planet.
Mm-hmm.
So all life as we know it has been shaped by the nature of this body. And we have profoundly changed the planet. The planet has profoundly changed life.
Yep.
So I think we need to first explore robotically to see if there's anything native there. And then I'm not sure how long it will be before we understand the power of coevolution and can create organisms that would be well suited to the environment in which they're going to be placed. It may be easier, and it certainly was what we talked about first, it may be easier to transform the environment so that it suits the organisms that we might send. So terraforming planets, for example. I think it's going to be a very daunting task to understand the boundaries of the biome that we might have to create on another world so that organisms that we send can thrive. Synthetic biology may get us there. I used to think that indeed, in order to understand what was necessary and what is contingent in life as we know it, it would require us to find another example of biology that evolved on a different planet in order to see what was absolutely necessary and what was just so. That's the way it happened here. But maybe, in fact, synthetic biology can get us there and open up this spectrum of possibilities of different ways of changing chemistry into biology. Don't know. It's one of the reasons that I'm ticked off that I'm so old, right? Because I think that the 20th century was the century of physics. The 21st century is going to be the century of biology, but I think it's going to be the century of biology on Earth and beyond. And I'm just not going to be around to see all the wonderful beyond things that we learn.
If I could spend some of my infinity dollars today and put Dr. Jill Tarter on the spaceship that I've been building in my backyard here, where would you like to safely explore in our local planetary neighborhood? Moons of Saturn, Mars. If you could dig, hang out safely for a while, what do you think the action is in our neighborhood?
I'm really intrigued by Enceladus, right? Those cryovolcanoes coming out of the South Pole are extraordinarily interesting to me. And in addition to Europa, where missions are planned, we are beginning to talk about a flyby mission through the plumes of Enceladus to see what's coming. I mean, that's sampling the oceans that are underneath that icy crust and to see what might be there. I think that's really intriguing. And of course, Mars, the thing about Mars is for all of these years, every time we thought we understood something, we've been wrong. We've gotten Mars wrong over and over again. So we now know with the that there is liquid water near the surface of Mars with these recurrent slope linii. are there indeed underground water sources where life might in fact still be extant? You know, we're talking about looking for fossils, looking for extinct life, but now, you know, we've had to rethink our surface exploration protocol with this near surface water.
Mm-hmm.
We used to think that, well, it didn't matter. We took microbes to Mars, they wouldn't survive the surface, right? And so we wouldn't necessarily be confused by finding life that we brought ourselves. But now that we're finding that there's this liquid environment, that's, you know, we might in fact bring microbes that could find a way to survive, and that would be confusing. And so we have to do a better job. Things are getting more interesting.
Absolutely. Joe, one final question, and this is a little more esoteric, but, and I don't know if I have to phrase this the right way, but in your scanning of the cosmos over the years, have there been ever interesting anomalies, signals that have come back that don't emanate from a star or an exoplanet, which cannot be at this point, or, you know, wow, that was an interesting signal, but there's nothing there, or maybe it was a comet that shot. It's something that's not what we would think of. Okay, there's only a planet here that's something's happening on, or a star giving off X, Y, and Z. Any weird anomalies in the sky, in the cosmos, that you know, oh, wow, you put that on the side, and you'll come back to it later. It's weird. And I don't know if you see where I'm going. I know I'm getting a little esoteric here, but you know, we've talked to some folks in the past just about, you know, there's all these concepts about information in the universe, previous universes, before the Big Bang, things of this nature, cosmic background radiation, so forth. Any other really interesting but weird findings over the years from SETI?
Well, not from the SETI Institute, because we have designed our search protocol so that we use more than one telescope simultaneously, so that we do our signal processing in near real time.
Okay.
And that allows us the ability to immediately follow up and try and figure out what it is we've detected. And nevertheless, we have had intriguing false positives.
Okay.
All right. And they have particularly occurred when one of our telescopes is out of commission. So there's a temptation, because you have to apply for telescope time, and it's very precious as we use these large instruments around the world. If the second telescope goes off the air, you still have the first one, and you don't want to waste the time. So it's tempting to go ahead and continue to observe with a new strategy where you look at the target and look away from the target. It's a standard technique for radio astronomers. And it's been those occasions where we have had these strange false positives. Now, in every case, we've been able to show that the signal is actually not coming from the star. And in most cases, we've been able to show what it is, and it's been our technology.
Okay.
And I think the most intriguing one turned out to be the SOHO spacecraft in orbit around the sun, rather than in orbit around the... Other groups end up finding signals in their data, and they really can't do anything. I mean, they go back and reobserve, but it's months or years later, and they don't find it. So what does that mean? I'm starting to ride a hobby horse, that I think that going forward, we really ought to be thinking about observing protocols that lead to verifiability, right? So that if you find something, then you absolutely know it's there. And so for me, that means multiple telescopes observing simultaneously, among other things. And I think about the WOW signal. And if I had been running that project, you would never have heard about the WOW signal, because they had a built-in protocol. They had two receivers, east and west. They expected something coming from the sky to go through the east receiver, fade away, then be picked up by the west receiver. Well, their computing was so primitive that, in fact, they know that the signal was picked up in one receiver, but they don't know which one, because they were only printing out the difference between the receivers' voltages. And a lot of time has been spent speculating about that signal. A lot of telescope time has been used to reobserve one of the two positions on the sky that the signal might have come from. And I think that's all not very helpful. I think that this is such a big question, and if that you're going to make an announcement, you really have to have credible observational results, because it is going to cause a lot of change in the world. And you don't want to be crying wolf. You don't want to not be able to stand up and say, this is how I know it's real. So we'll see.
You will.
You notice that I have an array, right? Not just one telescope.
That's true. Joe,
the spatial location that you can, using interferometry or pseudo interferometry, as we did in Phoenix for all those years, the spatial localization you can get from widely separated telescopes is going to be extremely useful to figuring out whether or not this is what you're looking for.
Joe, one final question while I have you, and I really appreciate the time you spent with me. Obviously you do a lot of work on the education front, teaching, outreach. We always get feedback on these shows, and I know I'm going to get a lot with this one from students, maybe high school seniors to starting headed to college, maybe some freshmen. They want to be Joe Tarter. They want to follow in your footsteps. They want to, take this to the next generation. Some recommendations for them. What should they be studying? Should they be working in astronomy, the geoscience side, the biology? What are you looking? Once again, we have infinity dollars. We're building up the SETI project. What type of folks do you want knocking on the door 4 years from now when they're finishing their PhDs 10 years from now? Give a little advice if you could.
My only advice is to find something they really like doing, right? Something that they enjoy, and then go to school for as long as it takes to get to be the best at doing that thing of anybody on the planet. And now they've got a tool, and they can look around and they can try and find what questions, what problems are of interest that they can apply their tool to. And I think, given that, well, first of all, as opposed to my generation, they're probably going to not just have one job during their career, they're going to do many different things. So having a tool that allows them to be flexible and attack this kind of problem or that kind of problem, whatever pleases them, I think is the right way to go. It will serve them well in terms of their future careers, and it will probably serve SETI very well too, because we don't yet know what the right thing to be looking for is. And they might, in fact, expose to us some new idea that makes sense, the zeta rays that I always talk about. Right? And so if they are well trained, well educated, and well skilled then I want them. And I want them to be deciding what new direction we might want to go. Right? So that's the best advice I can give.
Excellent advice. For everybody listening to this episode on the podcast network, or obviously watching on the YouTube channel, you've been listening to the amazing Dr. Jill Tarter, Chair Emeritus for SETI Research at the SETI Institute, exploring, understanding, explaining the origin and nature of life in our universe, inspiring future generations. Pick up the book, Making Contact, Jill Tarter and the Search for Extraterrestrial Intelligence, to learn more about everything she's done throughout her career. Jill, it's been a real honor having you on the show, and I want to thank you for taking the time out of your schedule. Thank you for sharing your knowledge with us, and as we say, thank you for helping to create a better tomorrow for all of us through your work. It's so inspiring, and really, once again, appreciating your time.
Thanks, Ira. It's been fun. And what you've missed, because it's behind the screen, is the squirrels that we feed here in the Berkeley Hills, who have been hanging by their hind legs, peering down through the window at me, trying to tell me that they're out of nuts.
We have city squirrels here in Philadelphia, but they don't knock on the window.
These guys are really persistent, and they just get right in your face and they say, "Come on, lady, let's get some more nuts."
I'll let you get back to it. Thanks so much, Jill.
Bye, Ira.